we're almost done. We have a continuous function. If you have some portion of its domain being connected, when you look at just that portion and you map it over, f of e is also going to be connected. The way we prove that is we look at f of e, that big black blob there, and suppose we can split it into two different chunks. We have an a and a b that are just, both a and b are non-empty, but their intersection is non-empty, and f of e is equal to a union b. To prove that's connected, I'm going to find a sequence that lies in one but converges to something in the other. And the way I find that sequence, well, f of e came from this black blob over here, e. And similarly, b came from this purple blob over here, d, and a came from this red blob over here, c. And I know that e is connected, so e is equal to c intersect d, c intersect d has to be non-empty, and also c and d both are non-empty themselves. So since I know that e is connected, that's part of my hypothesis, I know that there's a sequence, barely legible, but I've got this green sequence of dots, x1, x2, x3, that is all inside, say, c, the red circle, but it converges to something in d, the purple circle. So that's why I said over here, x of n belongs to c, but it converges x, which is in d. That's what's going to give me this yellow sequence over here that I need, right? Because I know for sure that, maybe I'll do this in black. I know for sure that x is in d. What does d mean? If x is in d, that means that f of x belongs to b. So this means that f of x belongs to b. But the xn are all in c. And if xn is in c, that means that f of xn belongs to a. So f of xn belongs to a, just plain old a. So if I look at the sequence f of x of n, that completely is contained within a, but it's going to converge to f of x, which is in b. And now the last thing is, how do I know it converges to f of x? Well, this is because, in fact, I'll write this down. The sequence f sub x of n converges to f of x, since this is only true because f is continuous at x. It's continuous everywhere, so in particular it's continuous in x. So that's just a basic thing about continuity. Right? A function is continuous at a point x if every single sequence that converges to x has the property that f of that sequence converges to f of x. So that's the basic fact about continuity. So that gives us our yellow sequence. Here are our f of x of n, which I'm calling y sub n, and that converges to y, which is equal to, I can let y be equal to f of x. So I have a sequence that lives entirely in a, but it converges to something in b, which means that f of e has to be connected. That's the basic idea of the proof. I just take f of e, split it into two disjoint parts, and I need to find a sequence that lies entirely with one but converges to something in the other. And the way I get that is I map back to E and split that up into the two corresponding parts, the pre-images we call them. Find a sequence that lives entirely within one but converges to something in the other. Now I map that sequence back and that limit back, and I get f of x of n lives entirely within A, but f of x lives entirely within B. And of course, if the sequence x of n were actually in D instead of C, well then it just switches and you get f of x of n belongs to entirely within B, but f of x is in A, so it can go either way. We are finally done with this. Have a good day.